All right, hello everybody. Today we're going to talk a little bit about sampling, and in particular, or what I'm going to do with this lecture is I'm going to try to break it down into three different videos because the whole thing will probably be way too long. So for this first video, what I want to talk about are just the concept of sampling to begin with, and then I want to walk you through a few demos of sampling in R so you can see how it works. Before I get into that, though, I want to address something that I kind of talked about a little bit inadvertently in the last lecture that I made for this series. But last time we looked at people's heights, and I walked you through sort of the z-scores for the different heights in the people who had taken this class over the years. And we found that it kind of basically forms a normal distribution, which is interesting. And it's a funny thing because, there are people who are just people from wherever and happen to be connected by this class. And then it turns out that their heights have this distribution. So I kind of inadvertently hinted that there might be some puppeteer placing us all in the right spots on a normal curve. I didn't want to mislead anybody by the idea that you might take that too seriously, basically. So it's not necessarily, there's nothing intentional going on with our heights. There's different forces that determine how tall we are, and more or less, right? And it's not necessarily some intelligence making it all happen in the end. And with that in mind, I kind of wanted to address one of the fundamental issues of this class, which is the idea that it's hard to distinguish between something going on and nothing going on. With that in mind, I'm going to show you a couple of videos. And the first one of these is something I picked up a long time ago. It's a video from New Brunswick where a guy is out in his backyard and for some reason filming the clouds. And let me open this up. So let's see if we can get to it. We'll watch it for a little bit. Let's do a restart here. Okay, so here's... I have no idea what he just said that. Maybe you heard it, maybe you didn't. It didn't sound like English. And New Brunswick is actually the only province in Canada which is officially bilingual in terms of being both English and French, but it didn't sound like French either. And another thing this guy does, which, I might do, but it's not something I commonly do, is that there's a thunderstorm rolling in and he's just filming the clouds in his backyard, which I can admire. And something interesting happens here. So here we go a little bit further into the video, and I'll just let it play out.
Face. Holy freak.
Okay, so I'll stop it there. But hopefully you can see what looks like a human face here with like a forehead and like the eyes, and this looks like the nose and mouth and chin. It's all there. There's even what looks to be like ears here. But this might, if you look at it this way, it might be like, vampire face or something from that like Francis Ford Coppola vampire movie. Anyways, because those are pretty serious ears. Yeah, so it looks like a face, right? There's obviously not actually a human face in the clouds, but you can see it. This guy can see it. We all can kind of see it. Our minds are tuned in to recognizing human faces for really good biological and practical reasons, right? It's important to keep an eye on the weather when it's stormy out, right? But there's nothing more important in our lives or in our environments than human beings, right? And so if we see somebody, we need to recognize that they're human, and all the things that human beings can do follow from that, right? It's interesting too, like this is something that, maybe the switch flipped automatically in your head once this thing started to look sort of like a face, and then you saw the pattern in it. And it's hard to resist the temptation to say, oh, no, it's just not a face. It's just like random cloud formations. I talk about this a bit in my advanced phonetics class, but, some people hypothesize that we have what are called modules in our heads, which are sort of bits and pieces of the brain, which are biologically specialized to identify certain aspects or certain features of our environment, or deal rather with certain sort of types of information we get from our environment. And interestingly enough, there's evidence that there is basically a module of sorts in our brains for recognizing human faces, because there are some people who do not have that ability, and they might lose it through brain damage or something like that, or a stroke, or what have you. And when you get that condition, it's called prosopagnosia. And so there was actually a famous neurologist named Oliver Sacks who wrote a number of books for public consumption, which are sort of fascinating to read, who had this condition, even though, he's a very intelligent man, and he understood the brain as well as anybody, basically, but he could not recognize his wife's face. So, like, if he saw and it's kind of tragic when you think about it, but when he saw his wife, he wouldn't be able to recognize that it was her until he looked at, like, the other cues that were provided to him by, like, her clothes or her shoes or the shape of her hands or something like that. He couldn't look at her face and say, that's my wife. And if he looked at her in the face, he would say, she has, like, blue eyes, or, like, a narrow chin or something like that. He could describe the features of it, but he just couldn't put it all together because there's a part of his brain that wasn't doing that job. So anyways, I'm getting a bit far afield by talking about this, but we're human beings. We bring certain biases into any sort of objective analysis, or any attempt to objectively analyze what's going on in our environments. And there, like I said, there are good biological reasons for that. We need to know more about what human beings are doing than what we need to know about what the weather is doing. So part of the goal with statistics is to get beyond that bias as much as we possibly can. And that's kind of a general goal of science as well, right? What is objectively going on in the world, independently of what we may think about it. So, if you see a pattern emerge in the world, like a distribution of heights shaped in a certain way, it's easy to get a temptation to say, well, nature or God or whatever is trying to put things in this order. And, maybe that's possibly true, maybe it's not. But as scientific statisticians, one of the things we have to do is sort of commit to the idea that nothing is intentional in that fashion. Nothing is trying to happen in that way. And what would the world look like if that's the case? And assuming, at least to a certain level, that nothing is going on, does the world look different from the way it looks like if nothing were going on, right? So a pattern like this in the clouds, there's lots of randomness in these cloud formations. There's lots of forces we don't have a record of or totally understand what's going on. Just, stuff happens in a cloud, and stuff like this phase can emerge through just randomness over time. It doesn't happen that often, but it happens every once in a while, right? I'll show you another example of sort of that sort of patterns like that emerging through randomness or other forces besides sort of intentionality. So this is a device that's known as a Quincunx, which is a funny name. It must be from Latin. I don't know the derivation of it. Let's pause here. So this is some, I don't know, it looks like some scientific conference. This guy is James. He's apparently from the University of Cambridge, and he's going to pour a bunch of marbles or something into this Quincunx, and we'll see what happens. Yeah, so this takes a while, so I might as well try to walk you through it a bit. But basically, the marbles go into, it looks like Plinko from The Price is Right or something like that, but it goes into this device, and, it hits the tops of these red knobs, and at each point, they kind of have to choose whether they're going to one side or the other. And you could say for each one of these red knobs, that choice is made basically randomly. And over a series of choices for a certain number of knobs, I think I counted there's 12 down here on the bottom, an even dozen. Sometimes they're going to go one way, sometimes they're going to go the other. Actually, ideally, sort of half and half with a bit of randomness thrown in, right? It's all randomness on top of this structure, and what emerges out of that is this nice normal distribution pattern. And you can kind of think of our heights as operating in a similar fashion, right? Somehow this wound up being slow motion. I don't know why that happened, but we're going to get a goofy smile here from James. Thank you, James. It's a science festival at the University of Cambridge. That's what it was. It wasn't a conference. It wasn't a fair. It was a festival. Anyways, way better than Fire Festival. So, right, you can get structure out of a minimum number of constraints and randomness thrown on top of it, right? It doesn't need to be like an intentional pattern that something is trying to put together. That's the only thing I want to sort of really clarify there. That being said, there's sort of a world of complete randomness out there. And then we know that there are actually structures in the universe, and we're just trying to identify where the structures exist. And the way we're going to do it is to make sure that they look meaningfully different from the underlying randomness in the universe. So that's getting a little bit ahead of ourselves for the moment. But for the most part, you can describe heights or the normal distribution of heights primarily based on randomness with a few other sort of biological constraints. And you don't need any sort of intentionality to make it happen. But it's interesting that we get those sort of connections. They're not obvious on the surface, I guess, is the main point of the original point I was trying to make. And we're going to look further as we go through this into sort of how can we identify a difference between nothing and something as we go. But we need to do some groundwork before that can happen. And the first part of that groundwork is going to be analyzing how sampling works. Okay, so much for that. Let's stop being normal. Let's briefly consider a non-normal distribution. And the non-normal distribution that I want to think about is the distribution you'd get for dice rolls. So I've got a die here. I've got two dice actually, and they're both D6s as opposed to this D12, which has 12 sides to it. So we've all seen dice like this, hopefully, or presumably in our lives. I don't know how easy that is to see, and you can roll them. And I might actually show you the results here, but I got a 6 in this particular one, right? So if I'm rolling dice a lot, like what sort of results am I going to get? We've talked about this before. What does the distribution of dice rolls look like? On top of that, you can answer these questions. I normally ask these questions in class and wait for people to answer them. So think about the answers. What is the mean of the distribution of dice rolls that we get? And then what is the standard deviation of those dice rolls? Think about it for a second. I'm going to take a drink of water. Yeah, what are the answers to these questions? You should be able to figure them out based on what we know. It might take you a little bit of mathematical work to get there. But the distribution is going to be uniform, ideally. So we've got 6 sides to this die. And if it's a fair die, if it consistently, randomly winds up on one side or the other, we should be able to get all 6 results more or less evenly across the board, right? So that's a uniform distribution. The mean of the distribution is going to be the values of those 6 sides from 1 to 6. Divide all those by 6 because there are 6 sides. And then sort of the average is 21 on the top. That's the sum of all these numbers divided by 6, which is 3.5. So if you roll a die, on average, you'll get a value of 3.5. I got 5. Before I had 5 and a 1 together. So the average of those two is 3. Now I've got 5 and a 1. That's 11. Divide that by 3, you get what? 3 2/3. So we're getting close to that mean, right? If you do it enough times, trust me, it'll get there. It may be trickier to find out or figure out what the standard deviation is. And again, normally I ask this question in class basically to kind of review for people how to calculate standard deviation, because this is a relatively easy math problem, relatively speaking. So if you understand standard deviation and don't want to walk through that demo again, you can skip ahead if you'd like. Otherwise, I'm going to do it for everybody else and just show you how this works. So here's our equation for standard deviation. We've got the sum of squared differences here in the numerator of the equation, and we've got the degrees of freedom down here in the denominator. This is the equation for variance, sum of squares over the degrees of freedom. You take the ratio of those and then take the square root of the whole thing. How do we do that for dice rolls? Well, we have 6 different values we can get out of the dice rolls. And I'll walk you through this first example. So we know now that the mean or the average value of a dice roll is 3.5, or a die roll is 3.5. The difference between 1 and 3.5 is negative 2.5. If I square that, I get 6.25. Moving on up the scale, we can do similar things for 2. The difference there is negative 1.5. The square of that is 2.25. For 3, the difference is negative 0.5, and the square of that is 0.25. And what we'll see as we go to the end of the possible outcomes of a die roll is that we get a symmetrical sort of pattern here, that the squared differences all kind of match up with the ones we saw on the lower end of the scale. And then so what I want to do here is sum up all of these guys here in the right-hand column. And maybe you can do that in your head real quick. Maybe you can't. It doesn't really matter because I'm going to do it for you. The sum is 17 and a half by the time you get to the end of all 6 possibilities. Okay, so that's our sum. We need to divide that by the degrees of freedom and then take the square root of that ratio. So our degrees of freedom, there are 6 possible outcomes, but we know the mean. So that reduces the number of degrees of freedom by 1. So we get 5 degrees of freedom. What is 17 and a half divided by 5? It turns out it's 3.5. There's that number again. That's the variance of this distribution. If I take the square root of that, I get 1.87. And again, I'll just mention in passing, it's kind of funny that the mean and the variance for this distribution are the same value, 3.5. That's just kind of coincidence, though. What we'd care about more, what I asked you about more specifically, is the standard deviation, which is the square root of that. It's 1.87. Okay, that's just some technical background, but we have now a sense of what these parameters look like for the distribution of dice rolls, which is a non-normal distribution. Okay, so let's move on from there and say what happens when we take a sample of dice rolls. Before I had a brief sample where I just rolled these 2 dice. And that's what I mean by a sample of dice rolls. Let's roll these things and see what values we get. So before, our 2 values in our sample of dice rolls was 5 and a 1. Let's do this in R. It's pretty easy to do that. And it's kind of fun too. So, I mean, I know we all like to play dice rolling games, but it's easier if a computer does it, especially if you're doing a lot of dice rolls. And let's sample 2 at a time and then calculate their mean and standard deviation. So I'm going to walk you through how to do this. You can roll 2 dice in R like this using this sample command. So that's the general command with the different parameters in parentheses here. I'm going to make this a little bit bigger so you can maybe see it better. So what this does here is the 1:6 says basically choose from the values 1 through 6, which is the set of numbers on a die, and pick 2 of those, or do it twice, really. And then it also gives you this parameter replace equals true, or replace equals capital T. So what that means is that after I roll 1 die and I get, like, say, a 5, then make a record of the 5 and then put the 5 back into the mix so that when you do it the second time, you're also still choosing from the values 1 through 6. So yeah, if I weren't going to do that, then if I rolled the die a second time, then 5 would not be an option. So if I do it like without that replace equals T, if I do just 1 through 6 and then 2, I'm never going to get the same number twice. I'm always going to get different numbers. So let's try it with that replace equals T. It might take a little while, but eventually we'll get the same number twice. Might get the same pair of numbers twice. This is taking longer than I thought. This is like rolling doubles in Monopoly. There we go, 5 and a 5, whatever that's worth. Roll again. Okay, just don't roll it 3 times in a row. Oh, good, I don't have to go to jail. Okay, so there are your sample numbers. That's how you do it in R. It's pretty straightforward to calculate random numbers in that fashion. If I want to take the mean of any of those individual samples, I can do it like this. Just place this entire command within the mean command. And it's not going to tell me in this case what my values are, but I can maybe figure it out. So this mean is 4.5. So we either rolled 4 and a 5 or a 3 and a 6, something like that. But the average is 4.5. And it's simple to do that over and over again. If I want to take the standard deviation, well, let's see what happens. I just placed that entire command within the SD command, which tells me the standard deviation of that set of 2 numbers. In that case, I go 1.414. That's standard deviation, or square root of 2. That's square root of 2 over 2, so on and so forth. These are all going to be kind of from a limited set of possibilities. And they'll be over and over again, but you can see what the standard deviations look like. So actually, I'll go back up here. Remember, with the means, I said the ideal mean of a uniform distribution from 1 to 6 is 3.5. I never actually got 3.5 for any of these means. I never actually got 1.87, which is the square root of 3.5 for any of the standard deviation. So, the sample looks different from sort of the idealized reality, right? Let's. Oh yeah, you can plot a histogram too. I forgot about this. And you need to do this in sort of a specific way. Otherwise, it will look kind of ugly or hard to comprehend. So going back to this sample command, I'm rolling 2 dice. And then I want to create a histogram of that by placing that sample in this histogram command. And I'm going to specify that the breaks should be where you'd expect them to be for a die roll, right? So in between the integer numbers, so in between 0 and 1, in between 1 and 2, so on and so forth. If I do that, then it tells me in graphical form what values I got. So I rolled a 3 and a 6, okay? I can do that again, and this time I rolled a 1 and a 2. Or this time I rolled a 2 and a 5, so on and so forth. Yeah, so that's how you create a histogram out of that. Let's do this again. And let's look at the means. But we're not going to roll just 2 dice now. We're going to roll 20. And like I said, it'd be fun to roll 20 dice if you had them. It's easier to do it with R because you don't have to acquire the dice. That's a fair number of dice to get. And if I do this, I look at the means. Remember I said the sort of idealized mean for the overall distribution should be 3.5. I'm in certain cases I'm getting 3.5, but I'm not sort of as wildly variant from that as I was before with just rolling 2 dice, right? Here I had like 1.5s and 4.5s and so on and so forth. Here I'm kind of in the neighborhood of 3.5, generally speaking. I can also try that with the standard deviations. And remember I said the sort of underlying standard deviation is 1.87. Not exactly on top of that, but it's pretty close in a lot of cases. 1.5, 1.7, 1.6, so on and so forth. And also let's look at the histograms of 20 dice rolls. Yeah, so not uniform still. A lot of 1s. That's funny. Go figure. We'll do it again. Still not uniform, but what do you expect out of 20 dice rolls? Kind of there. Let's move on up the scale. Let's do it with 200 and see what happens. We'll look at all 3 of these different sort of outputs. All I'm changing here again are the number of times I rolled dice. So yeah, the mean is ideally 3.5, and I seem to be getting even closer to that as I roll a greater number of dice. The standard deviation should be about 1.87. Yeah, sort of. I'm seeing, even if I'm not right on top of 1.87, I'm seeing less variation amongst these standard deviation numbers as I was before. And also let's take a look at the histogram. And yeah, so it plots it in kind of a funny way. So this is the 1, and this is 2, this is 3. So there's no gap here, but there's a gap here. So that's not great. But it's looking a little bit closer to a uniform distribution where I get even numbers across the board for all of these. Hopefully you can kind of get that sense. And lastly, I'll do the same thing for 2000, and hopefully this hasn't gotten too boring by now. And I think you maybe can kind of see where this is going. The means are zeroing in on 3.5. We'll see what happens with the standard deviation. I have a feeling as I'm calculating standard deviation here that it might be zeroing in on a calculation of standard deviation that divides by 6 in terms of the degrees of freedom rather than 5. And actually, if I do that, let's just see, 17.5 divided by 6. No, sorry. Maybe I shouldn't mess around with this. Yeah, in fact, I should definitely not be messing around with this. But if I take the square root of these guys, if I know how to do it correctly, it's about 1.7. So I think I might be getting sort of a different calculation. That's not going to change. Why do you keep doing that, Steve? That's not going to change, but these guys should probably be close to that value. It's a little bit different from what I expected, but there's a reason for that. And then also let's look at the histograms for 2000 dice rolls. And if I just find this. Yeah, again, it's not perfectly uniform, but it's looking more uniform than it did before with lower numbers of dice in the roll. And there's always going to be one, that's a little bit bigger than the other, or vice versa, whatever. Okay, but we're getting closer to that idealized distribution. The more and more dice we roll is basically the idea. And again, sorry about this, but I do this demo in class where people actually roll dice because it's a little more fun that way. But I'm doing this independently from you, and online, so I have to adjust somehow. But basically what I want to focus on here, even though we didn't do this all together as a group, is that there are two patterns emerging from our little sampling demo. Number one, the means are less variable than the individual observations. So keep that in mind. Before, when we had like, we're just rolling 2 dice and we might get 4.5 as an average or 1.5. But with 2000, we're getting close to 3.5 every time. And the one thing that I didn't show you specifically is the means tend to fall on a more normal distribution than the individual observations. So I'm getting ahead of myself a little bit with that point. When we look at the overall distribution of dice rolls, the more dice we get, the more uniform it looks like. But the means themselves will tend to do something different. They're going to fall on a more normal distribution than the individual observations. The individual observations themselves are uniform. So I'm going to walk you through how to look at that in a different way here. But that's basically one of the unexpected findings of this sort of these sampling demos. And so as I walk you through how to show it, I want you to think, like, why wouldn't the means form the same sort of distribution as the underlying data forms? Why do you get sort of that conversion of the distribution shape? So I'll show it to you in a slightly different fashion. Give me a second. We're going to take a non-normal distribution. In particular, we're going to take our distribution of F0 values from the students in this class, or the previous students in this class. And then we're going to plot a histogram of the means of many different samples from that distribution. So I'll repeat this again because this is a weird thing to do. We're going to have a non-normal distribution, sort of underlyingly, and then we're going to take samples from that non-normal distribution and calculate the means of those samples. Then we're going to do that multiple times. We're going to take one sample, calculate the mean. We're going to take another sample, calculate the mean. Take another sample, calculate the mean. And take all those means and plot their distribution in a histogram. And what is that going to look like? Okay, generally speaking, the question we want to answer is, are we going to get a distribution that looks like our sort of underlying non-normal distribution, or will it be more of a normally distributed distribution? Okay, so as a reminder, here's what our F0 histogram looks like. It's not normal. We saw this previously, but we're getting a lot of F0 values down here between like 100 and 200 hertz. This includes tokens from both male and female speakers, so we're kind of averaging across both genders, and then we're getting this sort of long tail here on the right-hand side where you get really high F0s for whatever reason when you calculate F0 automatically in Prot. And just as a reminder as well, I produced this graph with these two commands. I'm going to do it again just to get this data into the system because I want to play around with it for this demo. But just reading in the F0 data and then plotting a histogram for it. So here we go. Going to grab this F0 data like this. That length never changes. So you can do this too if you want. And then I'm going to plot the histogram like this. And I'm going to get something that should look very similar to what you see in the slide, right? In fact, it's the exact same distribution. Okay, so this is kind of like our underlying distribution. When we were talking about dice rolls, like our underlying distribution ideally was just flat and uniform. Neither this nor that is a normal distribution, but we'll see what happens next. So I'm going to do some sampling at random from this F0 data set. I'm going to grab some of these values at random and calculate their means. Just to see what the means look like. Okay, so before we use this sample command to generate random numbers in R, like we were rolling dice, and a die is basically a randomness tool. In this case, what we're going to do is use that same sample command to sample from a data set like our F0 data. Okay, so here's the command I'm going to use. I'm going to walk you through the details of this a little bit. So, like, if I just have F0 data, where are we? Okay, so like if I just look at my F0 data, I've got information about the speaker, their F0 value for some word, and then their gender as well. Actually, it's not a word, it's an individual sample of F0 within that word production. And then I've matched each speaker up with their gender. So if I use this other command here, where I'm trying to sample from this F0 data, this should look relatively familiar. This might not. We talked about this early on in the semester when I was walking you through the basics of how to like play around with data frames in R. But this is basically saying, let's look at the F0 data frame, F0 data frame. And then what I want to tweak with this is what I'm putting in these square brackets. So it's saying basically what I want to do is pick rows out of this data frame, which is, this is all this stuff is coming before this comma. I'm not specifying anything about the columns I want, which would be over here, but I'm just saying, basically give me 5 random rows from the F0 data frame. And the way I can do that is n row of F0 data is basically the number of rows in this entire data frame. So rather than having like the numbers 1 through 6 here, like I'd have for a die roll, I'm just saying pick at random out of all the number of rows in this data frame and just do that 5 times. And I'm not replacing, in this case, I'm not using this feature of the command because I don't want to have the same row twice. I want to pick 5 unique rows. And then we'll see what happens there, right? It's like picking 5 random people on a busy street in New York City or something like that. So if I do that, it gives me 5 rows at random. I've got, in this particular case, 5 different, no, not 5 different speakers. I got Lisa twice. So it's not worried about that. It just got different numbers though, right? So these are the individual row numbers, and these are the F0 values, so on and so forth. And what I really want to zoom in on here are the different F0 values. Okay, so yeah, and I guess I'll show you as well. If you want to randomize the entire set, this is saying pick out of the number of rows and then do it that number of times, which is the number of rows in the data frame. And if I do that, it's just going to give me everything in some random order. That's not useful for us now, but if you want to randomize, if you want to use R to randomize, like you're stimulating an experiment or some other reason, it's easy to do. And you can just use the sample command to do it. Okay, so what I'm going to do now is to start storing some of this sampling information. We'll do it at first with this sample of F0 values. We'll store it all in a vector called S, because why not? I don't know if there's anything better to call it, but if I do that, I don't see the row information anymore. It just all gets piped into that vector S. And if I type S there, then now I've got, look, 5 different lines from the ones I had before. They're all there, and it's 5 lines, right? So if I keep doing that, I just keep getting 5 different lines. To determine the mean of a sample, I can do something similar to what I did before with the dice rolls. I put this entire command within the mean command itself, and I'll get an average value that looks like that. And actually, something I wanted to do before, just to give us a reference's sake, is what is the overall average or mean value of F0 for this entire data set? It's 176.16, whatever. So if I'm doing this for random samples, I might get close to that 176, but not necessarily right on the nose, right? This is sort of like what we were doing with the dice before. We're going to get, it may be in the neighborhood ideally, but it's never going to be exactly the same thing unless I take the whole data set. Okay, so with that background, what I want to do now is kind of get sophisticated with this, so to speak. And I want to generate a bunch of samples. I want to have independent samples from this underlying data set of F0 values. And I'm going to store the mean of each sample in a vector called means. So I walked you through the process conceptually. When I got into this at the start, we're going to do it officially now. And the way we get this set up is that I'm going to call means a vector. So maybe you have computer programming experience elsewhere and you've heard this sort of structure referred to as an array. That's how I like to think of it. It's specified as a vector here. Either way, I'll show you how it's going to work for us. So what we're going to do is set up a loop. And this is something you're also probably familiar with if you've taken any computer programming classes before. If you haven't, don't worry about it too much. Just show you what this looks like. So we've got this vector called means. And now I'm setting up this for loop. And what this does is it is sort of like creating one of those summation commands that we've seen before in our math or arithmetic for variance and standard deviation. And it's saying, give me this variable I, and just cycle through I 10 times, where you start out with I equals 1, and then each time you go through this series of commands, you add one more to I, and then you do the whole thing again. And you keep doing that until I reaches a value of 10. So basically this whole thing is saying, I want you to do the following set of commands 10 times. And then each time you do it, add 1 to this variable I so that it increases its value as you go through it. And the command we're going to have this loop do is this one. First of all, I got to hit return here. And I'll point out as well, at the end of this command, there's this curly bracket. So if I hit return, what's going to happen is something very subtle, but significant. So before in my R console, I've always gotten these sort of caret, like, I don't know actually what you call those. So there's a caret on the left hand of each line, which shows you where the cursor can go so you can enter a command. Yeah. I'm not getting that after I input a command which ends in this curly Q bracket. So instead of that, I'm getting a plus sign, which means R is expecting me to add further commands into it up until the point where I have another curly bracket facing the opposite direction, in which case it'll close off this for loop. So this for loop, again, it's going to do the following set of commands 10 times. And I can add more than one command in that sort of bracket pair. In this particular case, I'm just going to do one, keep it relatively simple. And so I'll hit return there, and then I'll close it off with this right-hand bracket. And then it'll go back to this cursor sort of prompt here on the left-hand side. So that's kind of the machinery of R, but what it's doing here in the middle is important. So what I've got here is this command, which should look relatively familiar. So I have my F0 data, and I'm sampling out of that, and it's saying grab out of the entire set of F0 data rows, and then give me 10 different rows, right? And actually something I failed to mention before is this comma 2 bit on the right-hand side of the square brackets for F0 data. What that's doing is it's specifying, give me the value of the second column in the F0 data frame, and which is the F0 number, basically, that we care about. So that's how I was able to get this mean or average information here, is by just taking the average of, like, say, these 5 values of F0. When I print out this command just by itself, it gives me what that average F0 value is, whether it's 215 or 145 or what have you. In this particular case, when I put that command here, it's going to spit that value over into this means vector. But that which mean value it sort of puts into that vector, it's going to go into different slots. So I'm going to create basically 10 different slots in this means vector or array. There's going to be a means 1. Which might be, say, like 215 hertz. And then after I go through that command, I'm going to add 1 to I. So the next time it'll be means sub 2, basically. I'm going to create or calculate another mean out of a different sample of rows. And that might be some different value, like 145. And then the next means will be means 3, so on and so forth. So I've already actually done all that by executing these commands here. And what I want to look at now is just what are these mean values, right? So I sampled from the F0 data frame 10 times, and each time I grabbed 10 rows out of the data frame, and I calculated their average value of their F0, and then I put that average value or that mean value into this array of means. And I got a slightly different F0 average each time I did that, right? So 174 to 163 to 210, so on and so forth. Okay, that's what I'm doing with those commands, and I'm sorry for all the talk, but that's how it works. And once you get the hang of it, it's relatively easy to do yourself as well. And another interesting thing I look at here is what is the mean of these means? Which is a funny thing to look at. So I'm taking averages of samples from this F0 data set, and then I'm doing that multiple times. And now I want to take the average of those averages. And I get 181. And I think we calculated the overall mean of our F0 data set is 176. So I'm kind of in the neighborhood of that with 181. These other means from these relatively small samples are sometimes close to 176, sometimes not so close. But this one's not too bad, right? Okay, so normally in class at this point, another thing I do is look at the histogram of these guys. And it looks like this. So again, our sort of underlying average value is 176. I've got a big bump here in this histogram of means, my sample means, around that value, and then there's some variance on the sides as well. It's not symmetric, it's not normal, but it's kind of in the neighborhood of being like a normal distribution. So normally in class, what I would have people do, or actually what I would have people do is watch me do this. I would have them tweak the different parameters in the sampling loop, both the sort of number of items selected for each sample, and then also the number of samples that you take and store. So I'll just do that a couple times here. So let's do 1,000. Let's just go straight to the good stuff. Let's do this 1,000 times, where we take 10 samples, and now we have a lot more means. We have 1,000 of them. What's our average of the averages? It's 176. That seems pretty close to what I had before. It's actually almost right on there. And what if I look at the histogram, if I do this 1,000 times? Yeah. What do you know? I wouldn't say it's exactly normal, but it's closer to normal than it was before. It still kind of has a tail up here. We've got one mean up here, which is actually around 300 or so, which is interesting. So it's a little bit skewed to the right, but it's a little bit more normal than it was before, seemingly. What if I tweak this in a different way? We'll do it. We'll go back to 10, and we'll grab 1,000 rows 10 times. And now I just have 10 means again. And hey, look at that. We're in the neighborhood of sort of the underlying mean. And what does the histogram look like? I think it's not exactly what I wanted to do. Actually, what happens if I do this? Oh, I know what happened. Never mind. I got to reset my vector because I have 1,000 in there. So now if I do means, there's nothing in there. And I want to go back. I want to just do this 10 times. Let's try this again. I'm going to select 1,000 items in each sample. And now what happens with my mean and means? 176.2. There's only 10 of them in there. If I draw a histogram, it shouldn't look like it did before. It's actually not super normal, right? This is a weird kind of looking distribution. It's, J-shaped, going that way. But, kind of centered around 176. Let's kind of do both, change both of those parameters. Let's do it the right way. So we're going to do this 1,000 times. Selecting 1,000 rows in each sample, and then closing that off. Now, if I look at my overall means, I've got 1,000 in there. What is my average of averages? It's quite close to the overall average. Very, very minimal difference. In fact, 176.13 to 176.169, so on and so forth. What if I look at the histogram? Now I've got some that's still not totally normal, but it's pretty close, right? So you want it to be symmetric on either side. It's kind of centered around 176. The tails look pretty nice. We've got this kind of bump around here, but whatever. Maybe I could plot that out with more breaks. It might look a little bit more symmetrical. I don't know. Yeah, maybe. That's pretty close to normal, right? A lot closer to normal than what we saw before. Where we're starting out from is this, and now we're getting something that looks like this. And this is weird, just to remind you what you were doing. We're taking samples from an underlying distribution of F0 values. We take one sample of 1,000 rows from that data frame, calculate the average. Then we go again. We reselect at random 1,000 rows from that data frame. We calculate the average. And we're putting all the averages in their own little vector or array. And then we plot the distribution of those averages. And when we plot the distribution of those averages, we get something that looks normal, more or less. But it doesn't look like the underlying distribution of F0 values. So that's kind of funny. So that's where we're at the moment. Here's another example I did before I even recorded this video. This one had 10,000 samples with 100 items in each sample. So not exactly what we did. We had 1,000 samples and 1,000 items in each sample, but this is more normal as well. So I'm going to end the video here, maybe unsatisfyingly, but just to keep the question buzzing in your mind. But what we're getting is this sort of pattern. In general, when you sample, the means of your samples are going to be less variable than the individual observations in the distribution. And then the second part of that is the means will tend to fall on a more normal distribution than the individual observations themselves. Okay, I'm going to stop there, talk about some principles of sampling next time. I'll see you soon.